Now, one reason why these are not true equilibrium reactions is because the product is solid, right? The two-thirds of you who did this already and the balance of you that do this on Monday, one of the things that you should note when you do the derivatives, when you make the derivatives, is that you get a solid product, right? So when you guys added the DNP yesterday, you got this orange precipitate. And whenever a solid forms in a reaction mixture, it's effectively coming out of equilibrium, right? So there again, it's Le Chatelier's principle working for you. As product is formed and it precipitates, it comes out of the equilibrium expression. And that means the equilibrium then is shifted further to product, more products made, that product precipitates, more products made, that product precipitates, and the cycle keeps on going until it runs out of steam. Right? So that's one reason why the DNP reaction leads to product, not quite exhaustively, but you get quite a good yield from it. Likewise, the semicarbazone. Once the reaction really gets established, and it takes a few minutes, right? Because you're mixing together solids. In that case, I'm letting you guys make your own reagent in the reaction mixture. And as the video says, you got to shake it vigorously, and you really, really do. And then you got to heat it for a few minutes. And it kind of depends upon which unknown you actually have as to how quickly the results occur. Right? For once, you guys are not all doing the exact same thing in lab. So there will be differences from one person to the next. Possibly even two of you in the same hood will have quite different results when you make the derivative. All right? But the same thing. Once the reaction really gets established and gets going, the product is solid, starts to precipitate out of the reaction mixture, drives the reaction forward. Okay? So some extra details to talk about. And I think that's about it. There's another reason for these reactions moving forward. Just like to explore that quickly. G stands for group. All right, it's another little abbreviation us organic chemists like to use. X is handy when you're talking about halogens. R, of course, stands for hydrocarbons. Well, now I got another one, G. So G, what is G in this particular case? Well, it's all those things we just looked at, like an OH in the case of hydroxylamine, like an NH2 in the case of hydrazine, like NH2 phenyl in the case of phenylhydrazine, right? So that's what G stands for. It's the other thing attached to the nitrogen. One thing to realize about all these that I've shown you so far, right? Just take a quick look again. When you make the product, you've got an OH, an NH2, and you got an N with this aromatic ring attached. They're all electron withdrawing groups, correct? They're all electronegative, so they're pulling electron density out of the system. So now let's go back to this. In order for this reaction to be easily reversible, what has to be true? What has to be true is that this step has to occur, right? Protonation of the nitrogen, right? You're looking at the reverse of the mechanisms that we just did. So the opposite of this reaction is one of the last steps. Loss of the proton from the nitrogen to take away charge. So the reverse mechanism would involve protonation of that nitrogen to establish a charge so that water could then attack the carbon, what looks like the carbonyl carbon. Make sense? So if G is electron withdrawing, what's that do to the basicity of the nitrogen, right? That's an acid-base reaction. H plus reacts with the nitrogen. It's an acid-base reaction. If G is electron withdrawing, then what's it doing to the basicity of that nitrogen? It's lowering it. And if that nitrogen is less basic, then this equilibrium stays more with the starting material than it does the product. Does that kind of make sense? Okay?